Good evening. My name is Gareth Chan. I'm one of the SD7 registrars on the KSS rotation, as well as one of the honorary clinical lecturers at Brighton Sussex Medical School. So welcome to my NHS on-call room. So for those of my colleagues who are junior to me but looking forward to being non-residential on call, you don't always get to go home and you get to enjoy the delights of an NHS on-call room. So thank you for the invitation from ORUK and Hannah Patel for me to talk to you about a brief introduction into medical statistics for an orthopaedic surgeon. So we'll try and keep this really simple and go through the basic concepts that underpin our statistical analysis of any data that we look at. So what we're going to overview, we're going to talk about what types of data, what is data, how we analyze that data, how we interpret some of those results, and some potential pitfalls in terms of that result interpretation. So when we have data, we can have an objective data, or we can have subjective data. So data that you can measure, such as age, time in theatre, blood loss, hemoglobin, and something that's more subjective in terms of data that is graded. So is someone an ASA 1 or an ASA 2, or is this fracture type 1, type 2, or type 3 fracture of whatever type? So when we think about data, we've got these two types of data that we need to consider. And then of that type of data, you have nominal data. So for example, on the left of your screen, whether we fix a hip fracture with a DHS, which is plates and screws, or whether we fix it with a nail, there's no ranking to that data. Arguably, there's nothing that's worse or better. So that's nominal data. Another example could be someone's gender. But then we have data that can be ordered. That's ordinal data. So, for example, this is a hip fracture. A Garden classification type 1 hip fracture is better or less severe than a Garden type 2, which is less severe and carries a lower ABN risk than a type 3, and up to type 4, which carries the highest risk. So actually, as you go up the order sequentially, you get worse. So you could argue that an ASA 1 is a better patient than an ASA 2, and better than a 3 or 4. Although that's a slightly contentious issue that sometimes people argue falls into the next type of data. It can also be your GCSE results, your grade 1, 2 to 8. That's ordered. And then you have continuous data. So continuous data is data that you can measure as an integer, as a whole or fraction of a number. So that could be, for example, time in theatre taken for us to put one of those DHSs or intramedullary nails in. So when we break down data type, we have qualitative and we have quantitative data. So your qualitative is that subjective data. So you're grading something. And then of that data, you can break it down into ordinal or nominal data. So ordinal, again, is data that has a rank to it, and nominal data is not got an order, it's got no rank, it's just A, B, and C. And you can neither argue that A is better than B or C is worse than A. You have a quantitative, that's data that you can measure. So that's continuous data that can be divided up, or discrete data. So how many numbers? So those are whole numbers. So for example, an example of discrete data is how many screws you've used to fix a fracture, whereas continuous data is how much time you spent putting in those screws. And that's really important when we come to consider what tests we do. So when we design studies, or when you look and read a study, start thinking about whether this data is qualitative or categorical data, or whether it's quantitative data. And whether this data is ordinal and has a rank, or whether it's continuous and it's on a scale. So for example, let's take this study. So this study looked at time to dislocation for different prostheses of implants that we use for hemiarthroplasty. Now, if you look at what this described, it described the median time to dislocation. So what is median? And we think back to our GCSE maths, we talk about mean, median, mode. But what is mean, median, mode? Mean, median, mode is a measure of central tendency. So that's how the data pulls around a central point. So data, if it's normally distributed, so forms a bell curve, there's an equal amount of data on one side of the mean, so an equal amount of data onto the other side of the mean, and it's got the same spread. That is a normally distributed or a symmetrical distribution. And in that case, you have the mean, median, and mode are all the same. They're the same figure. But very little data is truly normally distributed in medicine. And most of it has a skew. So it could be positively skewed. So that's when there's a range at one end, at the higher end. That's a positive skew. And at that point, the mode, median, and the mean can't be the same figure. So mode is going to be the peak of your crest as the most common number or most common measurement seen. Median is the 50th percentile digit that you find, or the absolute middle digit, and the arithmetic mean is spread across. And as you can see, with a skewed distribution, you can get a mean that is influenced, or an arithmetic mean that is influenced by a very few or very small number of digits. And then you can get a negatively skewed, where the data is tailed off at the beginning and it's essentially the reverse of a positively skewed data. And again, as you can see, the mean, arithmetic mean, is pulled to one side by that tail. So why is that important? So it's important when we look at injuries and when you want to classify things and you want to describe how common things happen. So for the injury on the left, which is a talar neck fracture, these things don't happen very often. So with a small sample, you can have very skewed data. And in that case, when you have a skewness to your data, you might want to consider using a median over a mean. Whereas for hip fracture, which is a really common injury, especially in the older patient, you have a bigger distribution of data and they're more likely or potentially centered around a normally distributed data. So a mean may be more appropriate in that instance. And this is an example that's outside of medicine. We look at income or disposable income across the UK. Now, we look at the mean income. The mean income is skewed well away from what we think the majority of patients are. And actually, it's sitting in the 7th decile of the data because it's being pulled out to the right by those really high earners to the right of the charts. Whereas actually, someone who's right in the middle, in the median, is actually significantly less well off than is potentially being demonstrated by the mean. So that shows the importance of choosing your measure of central tendency appropriately for the data set that you have. So then we want to know how spread out this data is around the mean. So we can use something called a variance. So variance is a measure of how much each data point spreads from the central mean, but it's not the same as a range. So it's really important to consider that. Range is the difference between your top and your bottom value, and your interquartile range is the 25th and 75th percentiles. That's your interquartile range. And then your standard deviation is the square root of variance, and you use that for normally distributed data. And we'll touch on what we use standard deviation for later on. So when you have a low variance data or low standard deviation to your data, the red data, we know your data is pooled around a tight average, and we can be more confident in our measurements that they truly reflect the population we are studying. You've got to remember, every study is a study on a snapshot sample of the population of interest. We don't measure the whole population. Just think back to when during the COVID pandemic, when we tested a sample of the population to find the incidence and calculate that R number that we all grew to learn so much about. And then when you've got a big spread of data, is that true? It could be true. It could be, for example, patients' heights. Or is there a big spread because the sample of data we've collected from isn't actually big enough to get a true representation of the true population? So then when you start thinking now, when you're reading a paper, you'll read a paper and they'll start talking about statistical analysis. So then you read this phrase, statistical significance was accepted at p less than 0.05. But what is p? What is a p-value? When do we start using it? So we go back to the same paper and we look at the significance values. We get a p-value, and the cutoff for most orthopedic studies is the p-value of less than 0.05 or 5% is significant. And then look at the bottom of these tables, and normally tell you what tests they've done, and that relates back to the type of data that we talked about earlier. We'll touch on that later on. But touching a bit more on a p-value. So what is a p-value and why is it important? And we can base it around something called a null hypothesis. So a null hypothesis is a statement that you put at the start of your studies, and it states there's no difference between A versus B. Now, A versus B could be an implant, could be a treatment. So, for example, a study is there's no difference in outcomes when treating hip fractures with implant A versus implant B. Your study goes out to disprove that, and you set a p-value, and the p-value in orthopedics, as I said, is commonly 0.05 or 5%. But why is that important? So if we look at this table, this is something you may have come across before called a null hypothesis, and then look at the null hypothesis and a type 1 and type 2 error. So we all know what a false positive is when you falsely say there's something present when it actually isn't present, and a false negative is you falsely say something is not there when actually there is something there. And that's the same for a null hypothesis. So for example, if we reject the null hypothesis, so we say the hypothesis is saying there's no difference, and we reject that, so we're saying there is a difference, we can say that incorrectly, and that's type 1 error. And then the type 2 error is when there is no difference. When there is a difference and the null hypothesis is accepted, and that's a type 2 error. And you can think of it as an O.J. Simpson. So O.J. Simpson falsely acquitted, some would argue, of the murder in the 1980s, I believe. So are we falsely acquitting, or are we falsely rejecting the hypothesis that says there's no difference between these two groups? So type 1 error is when there's a false positive. So you're falsely saying that the null hypothesis is wrong and there is a difference when in fact there is no difference. And type 2 errors, and when you say the null hypothesis is true, so you say there's no difference, but in fact there is a difference, and there's an alpha or beta errors, and that's not really too important for your stage. But then where does this p-value come in? So we said the p-value we state is the risk that is essentially a chance to say that something occurs to chance. So there's a 5%, we're accepting a 5% risk that what we're seeing is due to chance. So if you reduce your p-value, you reduce your type 1 error risk. So by reducing it, you're less likely to have a false positive, because that figure that you have to get down to reject the null hypothesis is lower, and the percentage risk of a type 1 error goes down. But what's the problem? Then why don't we set every study at 0.01 or 0.02? When you look for such small differences, your significance value, then the number of patients you need to be confident in your results or to detect a difference goes up. And when the number goes up, the time taken to perform a study, and therefore the costs taken to perform the study, increases. But where what's in the p-value? What is a risk of 0.05? Taking you back to A-level GCSE maths, that's essentially equivalent to tossing four heads in a row, which gives you roughly a 6.25% chance. So it's roughly approximately that chance of saying something's occurring to chance. So when we look at tests, we have to consider whether the data is nominal or whether it's ordinal, or whether it's an integer. And we also have to consider whether it's parametric or non-parametric. And that goes back to looking at the spread of our data. Is the mean, median, mode the same? Does it have a bell curve? And non-parametric data is when it's not normally distributed, so non-Gaussian distribution, and that's when there's a tail one way or the other. And we can do that with those special statistical tests. And you've got Kolmogorov-Smirnov tests, and you can use histograms to plot it out. But again, that's not something that's we'll cover initially as an introduction to statistics. And this is a big table of data now. So what I'm going to do is turn my pointer on. So when you start your data, you've got to start thinking, is my data continuous data, or is it essentially not continuous data? Is it discrete? Is it groups? So if we're measuring age or a risk of death, for example, we then go down to our continuous data. So most data that measured on in terms of that we measure in orthopedics, in terms of time to theatre, days to death, length of stay, that's all continuous data. And then we think, is it normally distributed or is it skewed? With small samples under 50 is almost certainly not normally distributed. You can't assume normality in these groups, and you assume it's skewed. And if in doubt, you always assume your data is not normally distributed. And normally distributed, we follow it down the central portion. So we normally have two groups, or we have more than two groups. And then we talk about paired or unpaired measurements. So paired measurements are these measurements on the same group multiple times. You do a paired t-test. We do or if it's not, so it's two groups of patients with two different types of treatment. You're measuring time to death, for example. These aren't paired. These groups aren't related to each other. This is a standard t-test. And if you've got more than two groups, we use a test called ANOVA. And then when you've got a skewness to your data, most common is a Wilcoxon rank or signed rank test. If it's unpaired or paired data. And you move on to the other side of data. If it's all discrete or nominal or categorical data, nominal ordinal data, we then look at basically doing a chi-squared or Fisher's exact test. And that depends on how many numbers you have in each group. And if you have less than more than 5, it depends on, then it dictates which test you can do. So taking us back to a different paper now. So if you look at the paper, this is a study looking at periprosthetic fractures and the incidence of demographic differences in the patient groups. So this is a study that's looking at differences in patient characteristics in a study looking at different types of periprosthetic fractures. And we can see the asterisk, the cross here is for a chi-squared test, which is non-categorical data. So for categorical data, so that's nominal data. And this is if someone has osteoporosis, dementia, diabetes, this is all categorical testing. But then when we look at results, sometimes the results give us a 95% confidence interval. And we wonder, what is that when we read a 95% confidence interval? So 95% confidence interval is that you're certain that 95% of the likelihood the data will fall within this bell curve or within this range that you've been given. Now, 0 is commonly no difference. Minus and plus is one way or the other, better or worse. So if you're 95% certainty, that range that you're giving crosses 0, for example, here, then you can say, well, actually, what you're saying to me is you're 95% certain that the true answer in the population at whole is within this range, but this range includes 0. So you can't say there is certainly a difference one way or the other. So even if you found a true difference, so your p-value was less than 0.05, but your confidence interval crossed 0, then you can't say there's a true difference between whatever you're assessing. But then what is this 95% interval that we're talking about? And this is where our standard deviation comes in. And something called a 66, 95, 99.7, or the 1, 2, 3 rule. And it's basically how many standard deviations you are spread about the mean. So the greater you spread from the mean, the more standard deviations you include, the more certainty you have that the answer is going to be within that range. But as you can see, that range gets wider and wider and wider and wider. So when we look at results from studies, it's really important not just to look for your p-value, is there a difference, but also where people think or where the analysis tells us the true answer is likely to lie between. And most commonly, we use 95% confidence interval. That's a spread of 2 standard deviations around the mean. So that concludes this very, very brief initial introduction to medical statistics, orthopedics. We covered what data and what types of data we have. We've also covered how we analyze and how we pick tests in those to test that data. But we also covered where we draw the line and saying something is significant or not significant. Hopefully there'll be more sequence of these seminars to come. Hopefully there'll be more live. We talk about more specific tests and how they affect orthopedics. Thank you very much.